Alright, so we're going to do one more, I think this is going to be the last one, video in our complex numbers geometric intuition kind of series. Um, so last time we talked about how to do complex inner products with more than one component, right? So what we wanted to do is we said, all right, so we have like a1 plus a2 I, right, comma b1 plus b2 I, and then we multiplied that by, I'm just going to do that, c1 plus c2 I, and d1 plus d2 I, right? And then what we kind of did was we did this number times this number, the complex conjugate, and then we added that to this number times the complex conjugate of this number, right? And so this is two dimensions, right? So the first vector has two dimensions, and the second vector has two dimensions. So the what you can also do, I mean, you can do it 3 dimensions, 4 dimensions, you would just, take this one times this one, plus this one times this one, plus the next one times that one, plus, right? So now we're going to move it to functions, right? So we're going to start, and I wish I was better at graphing things. If I had, if I did it on a computer, it'd be a lot better. But basically what we're going to do today is find the inner product of two functions. So I'm drawing them like this. So the domain, look, we're going to do functions that are complex valued, but defined only on the reals, right? So let's call this t, and that's the real. And then we essentially have u and v. So it's almost like u1 of t plus, I want to draw that. So this is u. So this is function u. This is function v. So u1 plus u1 of t plus u2 of t times I, right? So you can see here, you're only a function of t, right? So this is your domain, but now you have your real axis and your complex axis. So like, so that would be sort of the positive real axis here, and then this is the complex axis, so that's I. This is the negative reals, and then this is the negative complex, right? And so then you have v1 of t plus v2 of t I, right? So I'm going to draw some function, right? And I'm not going to do great because it would look a lot better on a computer, but essentially, it's going to be some sort of corkscrew that like goes in this direction, right? I'm going to actually draw this one as a corkscrew, going along like that. And I hope that gives you some intuition of what these look like, right? And these are essentially only in the positive t direction, but they could go in the negative t direction as well. It doesn't matter. And so there's a few things. So kind of one way to think about what we're about to do is, how this is 2 dimensions, right? These are infinite dimensions, right? Because what you can do is you can sort of take a slice like this along t. You pick a t and you slice sort of this way. And then, so, if you draw this line, it's like, okay, maybe that is our complex value in that plane, right? It's just like, if you have a function, f of x, it looks like this. You take a slice along x, now you read that y value, right? But instead here, you're not reading a y value, you're reading a complex value. So you're reading like, 2 dimensions sort of. And then you could do the same thing here. So let's say this t is like 5. T equals 5. So let's pick about the same area. So let's draw this same plane that we're slicing along. And maybe this this complex number there. So we have two complex numbers that we're multiplying by each other, right? You can make this slice at any t. Same here. And basically how we do this is each slice, and there's infinitely many of them, right? You do this same trick that we did, right? To get the imaginary component, you take the cross product of the two, and then to get the real component, you can take the dot product of the two, which is the same thing as rotating by 90 and taking the cross. So I'm just gonna draw that one more time, right? So we've done t is 5, and then we've got one here. So what do these look like? They look like, so vector, let's call that one about like this. So that's v, or no, that one's u of t equals 5, right? And then this one, I think, looks about like that, right? And that is v of t equals 5. And so now we do it just like we've done in the past, right? Oh, sorry, I rotated that. So the imaginary component, we take the cross of the two. So let's see here. I'm going to draw it again like this. Looks something like that, something like this, right? And now we can drop down this perpendicular, something like here. And then, so this area here, this is the imaginary component. And then, so remember we do our squishing, so I think that's about 9 spaces, because maybe that's 3, so let's draw 9 high. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now I've been told to use more colors, and I think that's a good idea, so I'm gonna do that. So we're computing the imaginary, right? So this stuff here, and then this stuff here, these have the same area, right? And now what we do is we take this one and we rotate u by 90 degrees, so it's about right there. I'm going to shift this up a tiny bit. Rotate u by 90, so we've still got v looking about the same as v at t equals 5, v5, and then it's going to be rotated by 90. It looks about like that. That's u of 5 rotated. I don't know how I want to notate that. I'm just going to put a tilde there. And now you take the cross of these, so drop this perpendicular, looks about like this. And this shaded area, I'm going to say, is around 3. I wonder if you can see that yellow highlighting. Yeah, not very well. I'm going to change it to blue. So blue. That one's about 4. 1, 2, 3, 4. So now we're doing our squish. I said 3. I wrote 4 though. Sorry about that. So we're here now, right? So what that means is at this slice, t equals 5, right? That slice, this one times the complex conjugate of that is this new vector. And so now the cool thing is you can do this same process at every t, right? You would just slice it somewhere new, and then you'd multiply u times the conjugate of v, and multiplying u times the conjugate of v is the same thing as doing what we just did here, right? And that's what we've been talking about in the last few videos. So once you do that at every t, you get some new corkscrew. So this is t, and it's not always going to be a corkscrew, but that's kind of just one way to think about it. So you get just some new right here, right? And again, you could slice this at every time, but all you have to do now is just take the integral of this function. So this one is going to be yeah. So this isn't notation. This is actually what it is, right? It's u times v bar, right? And now all we have to do is take the integral of that, from t1 to t2. And what's actually happening there on these is to do an inner product, you can actually do it over whatever domain you want. Lots of times you'll see the inner product taken from negative infinity to infinity. So in that case, it'd go the whole length. But really, you can do it from any t or x you want. So like from there to there, all you'd be focusing on is this area, but that's fine. It's still an inner product. And the same thing happens in the reals, right? If you have, if you just have this function that goes on forever, and then another function that goes on forever, if you want to take their inner product, you can take it from negative infinity to infinity, but you could also just as well take it from here to here, right? That works too. So this is the final answer. Like this right here is equal to u times v, their inner product. And that's really all the intuition is. You just do our little process that we're used to. You just do it at every t value, and then you integrate this new function, which is exactly what you'd expect kind of when you think about it. So if you're integrating two real functions, I'll show you why it's the same thing, right? So let's get this ready. So if you have two real functions and you're trying to take the inner product of them, so let's say it looks like this, one function here, and then one function here. What you do is you multiply the function together at each point. So I don't know, maybe that's actually going to be a lot taller. Something like this. It's going to give you some new graph, and then all you do is integrate this one over the area that you want. If your inner product of f and g is defined by the integral from, I don't know, -4 to 3, then it's just f times g, right? That's all it really boils down to. And you might be thinking, okay, well in this one you multiplied the two, but in the other one you did all that, you did this weird process. But remember, this is the exact same thing as this, only this only has one dimension, right? Because, and I can show you, because this is basically only the real axis, right? So what's the cross product if both of these, like if you drew these in the imaginary plane, right? So let's take a slice here at about 3. So one function is maybe 2, one's 4, right? So in the real, or in the complex plane, one looks like this, it's this vector, and the other one looks like this vector, right? So we're here and here. So to get the imaginary component, you take the cross product of these. What is it? It's 0, right? Because they're in the same line. And then, to take the dot product, you can take the dot product, and that will give you the real component. And that's why only the real component exists, is because the dot product of these is non-zero. In fact, it's just 2 times 4. And so then your resulting function through this process is only going to have real values, whereas our resulting function in this process had complex values because they weren't, the original thing at each slice has more than one component. So yeah, that's that. And then in the next video, we'll do the same thing, but instead of complex functions, and that'll actually be the last video in the series, but in this one we have a complex function only defined on a real axis. In the next video, we'll do a complex function defined in the complex plane as well. So instead of u and v being only a function of t, now it'll be a function of, z, right? Because we'll have the z plane as our domain.